This is my Physics 2212 Experiment 4 on bar magnets. So the purpose of this experiment was to view the relationship between magnetic fields at varying distances while comparing our experimental data found in lab against computational results using GlowScript's Python model. There are a few physics principles and concepts that are important to understand for this experiment. One is magnetic field. What does it mean? What does it look like? 2, it's important to assume that the bar magnet is going to be considered a magnetic dipole. 3, we need to neglect the interference of metal objects on the magnet, like the table, which will be expounded on later in the experimental error section. 4, the magnetic dipole on axis and perpendicular to axis, which formulas can be seen here at the top on the right hand side of this page, and then the magnetic field of a magnetic dipole formula here at the bottom of the right hand side of this page. Quick little snapshot to our results. We're going to observe that the magnetic dipole moment is 0.90, which is what we calculated, and then you can see my experimental and my computational magnetic fields. This is a quick snapshot of my data table. This table was used and from the data collected in class. That off-axis field, dperp M, you can see that average of being about 0.17, and you can see all my other data points. Everything in yellow was found in lab. Everything else was calculated on the spreadsheet. These are 2 quick little snapshots of my Python and GlowScript model. As you can see us creating a function for the magnetic field and then adding arrows on our diagram and creating an arrow for the magnetic field at a 45-degree angle. So off of the axis, so for experimental error, and then we're going to talk about what happened. So in this experiment, we found a chip in an iPhone, which allowed us to align the magnetometer with the magnetic field of the Earth, so it would read 0. We align this with Earth's kind of north axis. We then measured on the axis the magnetic field at varying distances, 20, 70, 120, 170, and 220 microteslas. And then we measured the magnetic field off of the axis. So that's what we did in our procedure, in our experiment. So for experimental errors, we were able to see that the difference between our computational and our experimental models could have been due to the following. So 1 would be the interference of magnetic fields from outside sources like the table. Our experimental model, the wires that run through the tables in the physics labs could have affected our actual experimental data versus our computational model. That wasn't even considered. The placement of the phone, needing to realign it, and the error in realignment could have caused changes in the data. The error in application used to collect the measurements, so any in-app datas, we had to continuously close and completely reopen the app multiple times due to faulty readings. And some experimental questions. So what if that phone wasn't oriented and properly accounted for the magnetic north field? Well, then if it wasn't properly oriented, I believe that we would have got not only a Y component, but an X and Y component measurement instead of just that Y component. This makes it more tedious to compensate for Earth's magnetic field, and the calculations are just harder. So aligning the phone was very important during the experimental setup. And then what if we had 2 magnets that were stuck together end to end, and we ran this experiment again? What do we think would differ in our measurements? I would expect that the field would be twice as strong as it was before due to the 2 magnets being end to end. The measured distances for each magnetic field strength would increase, which, after calculating, would cause the magnetic field to be twice as strong as before.